A storm system larger than Earth disappeared so completely that one of the most trusted ideas in planetary science stopped working overnight. When the first high-resolution images of Neptune arrived from Voyager 2 in 1989, scientists saw exactly what they expected to find on a giant planet. A massive, dark, atmospheric structure dominating the southern hemisphere. Violent, stable, organized. It looked permanent, like Jupiter's famous long-lived storms. The assumption was simple. Giant planets build giant weather systems. And once those systems form, they stay there for decades. That assumption would not survive the next few years. The image itself looked impossible to ignore. Neptune, glowing deep blue against black space. A dark oval structure stretching across the planet, nearly the size of Earth. Winds racing around it at over 1,000 miles per hour. The coldest giant planet in the solar system, somehow producing one of the most organized storm systems ever observed. And right there, scientists thought they understood what they were looking at. They were wrong. At first, the discovery seemed straightforward. Neptune sits nearly 3 billion miles from the Sun. Surface temperatures plunge to almost minus 370 degrees Fahrenheit. Solar heating out there is weak enough that atmospheric systems should evolve slowly, very slowly. That giant dark storm fit perfectly into existing models. Cold environment, stable circulation, long-term atmospheric persistence. Then, years later, Hubble Space Telescope pointed back toward Neptune. And the storm was gone. Not weakened. Not shrinking. Gone. The new image showed the same blue planetary disk. Smooth. Empty. No trace of the massive structure Voyager had captured earlier. The visual contradiction was immediate. Side by side, images showed an Earth-sized storm system dominating Neptune in one frame and a completely blank atmosphere in the next. That was not supposed to happen. At first, researchers assumed observational error. Maybe viewing angle had changed. Maybe cloud structures were hiding the feature temporarily. Maybe the imaging systems were producing false contrast differences between the two observations. But that explanation lasted only until deeper atmospheric comparisons began. Because Neptune itself had not changed. The rotation remained consistent. Cloud bands were still visible. The atmosphere was still active. Only one thing had vanished. A planetary-scale storm system, large enough to swallow Earth, had somehow disappeared faster than every major model predicted possible. And that is where the real problem begins. For decades, planetary scientists treated giant planet atmospheres as relatively stable systems. Jupiter had already reinforced that belief. Its famous Great Red Spot had survived for centuries. Saturn's atmospheric cycles were predictable enough to map over long periods. Neptune was expected to behave the same way. Different chemistry, different temperature, same large-scale atmospheric logic. But the second those Hubble images arrived, reality began separating from prediction. The old thermal circulation models assumed energy movement inside Neptune operated slowly. Internal heat rises from deep beneath the atmosphere, interacting with weak solar radiation at the upper cloud layers. That process should create persistent atmospheric structures. But the vanished storm proved something dangerous. The energy transfer inside Neptune was moving much faster than anyone understood. And suddenly, this was no longer about one missing storm. It was about a failed planetary model. Because if internal heat movement could destabilize a structure that large in only a few years, scientists had fundamentally misunderstood how ice giant atmospheres actually function. And Neptune was not alone. The same assumptions had been quietly extended to Uranus and to theoretical models predicting weather behavior on giant exoplanets orbiting distant stars. Entire categories of atmospheric prediction had inherited the same hidden assumption. Cold planets evolve slowly. The Neptune images destroyed that idea instantly. But what happened next made the first disappearance even worse. Years after the original storm vanished, astronomers observed Neptune again. Another dark storm had formed. Not in the same place. Not following the same atmospheric pathways. An entirely new giant structure had emerged somewhere else on the planet. And then it started drifting unpredictably. The atmosphere was not stabilizing. It was reorganizing itself far faster than expected. The original Voyager image now meant something very different. Scientists had first interpreted it as evidence of atmospheric stability. Now it looked like evidence of extreme instability. The same image had changed meaning, and that forced a much larger realization. The outer solar system is not a slow environment. Not always. Even 3 billion miles from the Sun, planetary weather can reorganize violently on timescales short enough for humans to watch it happen. An Earth-sized storm had formed, collapsed, disappeared, and been replaced, all inside a fraction of a human lifetime. That means prediction itself had become unreliable. Because every atmospheric model built around slow planetary evolution now carried the same dangerous flaw. The deeper engine driving Neptune's weather was operating beyond observational control. The opening image said giant storms survive for decades. The second image erased that belief. That empty blue disk was not calm. It was evidence the model had already failed. Neptune changed first. The science changed after